Hey, welcome back to our second video for session 3 for our lesson 17.1 thermochemistry. So this video is going to focus on two terms, specific heat as well as heat capacity. And this is going to be more important next week. We're not going to do calculations this week, but we want you to be familiar with the term. So the word specific heat refers to the amount of heat it takes to raise the temperature of 1 gram of a pure substance by 1 degree Celsius. So just a reminder, a pure substance is something with a uniform composition. So that's only going to refer to pure elements as well as pure compounds such as water, H2O, that's a compound, and also silver, that's an element. Can't be used to calculate the specific heat of a mixture such as Chex Mix. So specific heat is represented by the symbol C of P. You might also see it as just C. I don't like using just C because C can be confused with the Celsius. We don't want to confuse it. So C of P stands for the specific heat of a particular substance. The P is there because it represents a standard pressure, a fixed pressure. So specific heat is also affected by pressure. We want to keep it constant. So at 1 atmosphere is what we refer to most of the specific heat values that we use in chemistry. The unit for specific heat is going to be joules divided by grams times degrees Celsius. And it's going to be constant for a given substance. So here in the yellow, we have how you would solve for a specific heat, which is useful to use whenever you're doing calorimetry problems, which is what we're going to focus on next week. So different substances have different values for specific heat. What that would imply is that different substances will require different amounts of energy to raise the temperature of 1 gram of substance by 1 degree Celsius. So the higher the specific heat is, the more energy it requires to change that 1 gram of substance by 1 degree Celsius. So here in this table, you can see the specific heat of a few common substances. That the highest specific heat on this table is going to be water, 4.18. And there's a specific reason for that I'll talk about in the next slide. Whereas solid water, ice, is actually 2.1. It has a different specific heat. And once again, I'll explain why on the next slide. And steam is 1.7. And all the way at the bottom, we have mercury. Mercury has a very low specific heat, 0.14 joules per gram degree Celsius. That means it takes 0.14 joules to raise 1 gram of mercury up by 1 degree Celsius. So it doesn't get to absorb as much energy as water before it starts heating up. So heat capacity. So this term right here refers to the amount of energy required to increase the temperature of an object by 1 degree Celsius. So the unit for heat capacity is going to be joules per degree Celsius, and it's dependent on the mass and the intrinsic properties of the object. So we like to use water as our example because we've talked about water time and time again. It has special properties because of its hydrogen bonding. Water has a higher heat capacity than other substances such as metal. So if you were to heat up 1 kilogram of water, it's going to take up much more energy than to heat up 1 kilogram of iron. So water is actually commonly used as a coolant due to its high heat capacity. So in the picture up here, we have a few steam chimneys. And you see this outside of a nuclear reactor because water is used to absorb the energy from nuclear reactions to generate energy. Water has generous heat capacity, so it can absorb a lot of energy, so it can cool down the reaction, keep the nuclear reactions from exploding and going out of control. This is also used for gaming PCs. So you might have a rigged up system where it uses water that flows through the chip, the motherboards, to cool the system. It's because water can absorb heat very well. Whereas if you were to use solid metal to absorb the energy, it's not going to do a really good job. So if you know the specific heat of your substance, so in this case, your substance will be your system, you can use it to calculate the heat of a system when the substance cools down or warms up using the following equation. So the equation's here in yellow. It's Q equals M times C of P times delta T. So to break it down, we're going to define the following symbols. We have Q, which represents the heat. Once again, going back to our first slide here, heat is used interchangeably with our change in enthalpy. And that's going to be equal to our mass mass is going to be in grams. So if you start off with kilograms or maybe ounces, you have to convert it to grams, multiplied by our specific heat, CFP, which is the units of joules per grams times degrees Celsius. So that's going to be the specific heat of your system. So if you're studying water that is warming up, that's going to be 4.18.